Good afternoon, everybody. Welcome back from Thanksgiving break. Hope you all had a good holiday. I just returned the exams that we took the Monday before Thanksgiving, and I have the statistics up here on the board or on the screen. You can find in this histogram your block. So they range from almost 100% down into the 30s. Most of the class was up here, which is a good place to be, I'd say. If you're down here, make some adjustments and try to do better. And but for the most part, people that are up in this range are doing from okay to good to very good. So overall, I think it was a good exam. There are 2 weeks left in the semester. So we've got this week and next week. And at the end of next week, Friday will be the last day of the semester, and then we'll take exam 4. So the fourth exam is 2 parts. The first part is new material that we're going to talk about in the next 5 lectures today, the rest of this week, and then Monday and Wednesday of next week. And then the other half of that exam is going to be review material from exams 1 through 3. So if you didn't get something right on one of the first 3 exams, you get another shot at it on exam 4. Now remember, you get to drop your lowest exam out of 4. So if you are in a situation where you've got one exam that's much lower than the other, and you can do better on that 4th exam than one of those previous 3 exams, your score will go up. The good news is exam 4 will not lower your percentage in Canvas. The way I've set it up is that nobody will get penalized for exam 4 at this point. Your score will only go up as a result of exam 4 or stay the same. So that's good news, and some people will elect to not take exam 4 if you've got a high enough percentage to get the grade you want. And you can look at your scores in Canvas too. I posted in the announcements the way to do it. So let me pull that up here and just give you a quick little synopsis of how that works. So under announcements, I have this announcement which says, exam 3 has been graded and recorded. It talks about how to do this. If you go to the grades tab and scroll all the way to the bottom, you will get a screen that looks something like this. Your numbers will be different. But at the very bottom, there are 2 lines. There's a CHEM 334 lab assignments. That's all of the lab assignments. If you're in the lab course, you can look and see what your lab assignment grades are. This is a test student that doesn't have any lab assignments. You could imagine this is a person that isn't enrolled in the lab, is just enrolled in the lecture, for example. But if you have lab assignments, you'll see the totals here, the points you've accumulated out of the possible. This is the line that most the people are going to be interested in here for the lecture. This is Chem 335 lecture assignments, and it gives a percentage and the points accumulated out of the points possible. And so this is a reflection of what your lecture grade is as of today. In this course, the lecture. There's a line at the bottom that says total. That's just a sum of the lab and lecture, but since these are separate courses, that line isn't meaningful, so I have X's through there just so you don't get confused by that. But what you can see here is test student has 762 points out of 972 possible. There's 1,000 points total in the course. That's 28 missing from the total. That's the ALEX homework assignments that we have yet to do. We've got one for chapter 22, which we're going to start today, and then we've got 2 assignments for chapter 20, which is going to be the focus of the last couple of weeks here. So then at the end of those, you'll have accumulated 1,000 possible points, and whatever your percentages is going to dictate where you fall in the grading scheme and affect what kind of grade you end up with. So you have some control over it if you do well on exam 4. If you want to do well on exam 4, I recommend you study for it. Going in and taking it cold probably isn't going to be very effective. So if most people have the capacity to increase their grade if they want to, but you'll need to work on exam 4 and study for it. So talk to me if you have any questions about this exam 3. The keys have been posted. If you don't understand something, let me know. We'll chat about it. If you have any concerns about exam 4, not sure what to do, I think the things I would do for exam 4 are obviously look at the new material, because that's half of the points. And then the other thing I would do for exam 4 is look back at your old exams 1, 2, and 3. And just check to make sure that there aren't any unresolved problems from those bits of theory that you haven't worked out yet. You know, hopefully when you get these exams back, you learn from any mistakes you might have made and you fix up that understanding. But if there's anything that's just not quite sitting well, let's get it worked out before exam 4. So, yes, question.
Will there be on like the 4th exam like a mix of like all the molecules of the day? Just gonna be none at all?
Question is about molecule of the day. There will be no old molecules of the day. I'll have like 3 new molecules of the day that I'll give you, but it'll be like an abbreviated molecule of the day section. But no reruns of molecules of the day from previous exams, because it's mostly, it's like pattern matching, and you've seen those before. So yeah, I'll give you some new ones, but it'll be a smaller amount of points. So good question. You'll have all the reference materials you've had on all the previous exams on that exam 4. So you'll get tables of spectroscopy data. You'll get all of the charts and like tables that I've given you for all the other exams. So there's going to be a lot of supporting information on that exam. So you'll have a lot of things to look at to help you, remember certain things. So any questions about exam 3 or exam 4? Oh, yes.
That's kind of a lab question, but
sure.
For the lab, should we meet in the classroom?
Okay, so this is a question about 334, the lab. So tomorrow is the last meeting of Chem 334, the lab that's closely associated with this lecture. Come to the classroom that you usually come to. I'll just brief you a little bit on what this lab practical exam is going to be like. The best thing to do is take a look at the old one, because it's going to be very similar to the one that was given last year in fall of 24, and that's posted in Canvas. So you can take a look at that and see exactly what kinds of questions were asked, and just kind of be mentally prepared for something kind of similar. Yes, another question.
Are we going to get that form that shows where the IR peaks are, kind of, so we can memorize those?
Yeah, so you can use on this lab practical exam that's coming tomorrow, you can use any of the reference materials that are in Canvas. So you can bring those up on one of the lab computers. If you have your own device, you can bring it up on there. Just access the Canvas site, and in there, in the supporting information are the tables of spectroscopy information in one of the appendices. And if anybody needs help finding any of that stuff, I can give you a hand too. So yep, you'll have all that stuff. You don't need to memorize those chemical shifts and peak frequencies, IR frequencies, and that kind of thing. So yep, that is available to you. So you'll be able to use all those Canvas resources, but just no AI chatbots or external websites or answer engines or anything like that. So that'll be tomorrow, and then after that, lab will be done. So we'll meet for the last time tomorrow in Chem 334. All right, any more questions? These are good. All right, well then we can get into talking about the new stuff, which is aldol condensation basically. So we had an experiment the week before we left for Thanksgiving, the week before Thanksgiving break. We did an experiment where we did an aldol reaction, and we talked about the theory briefly, and we're going to talk about it in some more detail now, though, so you can really understand what's going on with it and know how to predict the products of an aldol reaction and just decide how it's all going to work. All right, so this is chapter 22. We're kind of skipping ahead here a little bit. Chapter 20 is the next logical place to go, but I wanted to get this aldol stuff in early because I want to give you a bunch of time to think about it, and especially since we worked on it in the lab recently, I don't want to wait a long time on it. So we're going to talk about this, and these are just other kinds of carbonyl reactions. And specifically, the part we're going to look at is aldol reaction and dehydration. The theme is that carbonyls, we've looked at their reactivity as, let me just put this down here, aldehyde and ketone, just to refresh your memory as to what these things look like. Aldehyde and ketone. We've done a lot of discussing of reactivity where there's partial positive On the carbonyl carbon, partial negative. On the carbonyl oxygen, ketones are the same way. And nucleophiles like to come in and attack the carbonyl carbon. And if you've got something that has a lot of like positive character, like an acid, it can put a proton. For example, strong acids put a proton on the O. That's important stuff, but there's stuff that happens next door to the carbonyl too. And so we're going to talk today about how these positions that are next to the carbonyl are affected by it. So if you have an aldehyde or ketone, protons that are in this position called the alpha position, and I'll just put I'll put CH3 here because this is the aldehyde that we used in the lab experiment that we did. The position next to the carbonyl is called the alpha position, and then if you count further along, you can label other carbons along away from the carbonyl with Greek letters. So alpha is the first one, then beta is the next one, and then gamma and delta and epsilon and so on. But the alpha position, if there are any protons that are in this alpha position, they are weakly acidic. So alpha protons are weakly acidic. And if you put a strong enough base in with an aldehyde or ketone that has alpha protons like this, it can pluck one of those off. And that's how the whole aldol reaction starts. Here's an aldehyde that has an alpha position with protons on it. If you put a base like hydroxide in, hydroxide can abstract one of those protons, put a formal minus charge and a lone pair of electrons on the alpha carbon. There's a resonance structure that goes along with this, so you could take that pair of electrons and instead of having them on carbon, share them between these two carbons, and then a pair of electrons gets pushed up onto oxygen and you generate this different resonance structure. So these are both important structures for describing the nature of this deprotonated aldehyde intermediate. This thing has a name. It's called an enolate anion. So I'll put brackets around this to represent that they're resonance structures. And this is called an enolate anion. It gets that name from this resonance structure. The ene part is to specify that there's an alkene in it. The all part specifies that there's an alcohol in it, but the 8 part says it's protonated, so all 8s are deprotonated alcohols. So enolate is trying to say basically, here's a molecule that has a carbon-carbon double bond with an O attached to it that's deprotonated. So enolate. So you can see from the enolate that there's a lot of negative charge on the carbon and the alpha carbon, and also on the oxygen. And so that's the nature of these enolates. And any aldehyde or ketone that has alpha protons can get deprotonated and form an enolate. And that's where the process starts. So let's look at some different aldehydes and ketones and predict if they can form enolates or not. This was the one we used in lab, so it's a good place to start. But there are others as well. And there's homework questions that deal with this. The homework for chapter 22 is really short. There's only about a half a dozen questions, but they're good. And they should get you to, if you wanted more questions, you can always click the try another option too. So I didn't want to make it too short for you, but those are just the quality ones I could find. All right, let's take a look at an aldehyde like, or a ketone like this. Acetone. So if you put hydroxide in with acetone, there's an alpha position here that has protons, and there's an alpha position here that has protons. They can both get deprotonated, and since acetone is a symmetrical molecule, it doesn't really matter what side gets deprotonated. You get the same enolate anion. And I'll just draw this one. Is deprotonating on the right side. That's one resonance structure of this enolate. And the other resonance structure of the enolate is this one. Looks like that. And so both resonance structures are important. Do you know which one is probably more important? Could you predict? Like between these two, is there one that's maybe a little bit more important, describes the molecule a little better? Ooh. The one on the right, yeah, and that's because of where the minus charge is located. Yeah, the minus charge is on a more electronegative element here, so this is a better resonance structure than this one. Carbon holding a minus charge isn't as good as oxygen holding a minus charge. So they're both important. This one is more important. It's more like this, but this is the one that actually reacts in the aldol reaction, so we're gonna have to just keep track of that. All right, let's take a look at another kind of aldehyde or ketone, benzaldehyde. If you saw this on a homework assignment or an exam, could you draw an enolate structure for it? No. I guess what you'd want to do is you want to look at the alpha positions, the alpha carbons, and ask yourself, are there any protons there to abstract? And there is no alpha carbon on the right side. It's just a hydrogen there since this is an aldehyde. But here, that carbon has no H's. So there's no reaction here, no aldol or no enolate formation is possible. So some of the Alex questions, it might be, here's an aldehyde or ketone, and there'll be a box saying draw the enolate structure, and then there might be a little tiny box below that says click this box if you can't form an enolate, and this would be one example of that because there are no alpha protons. One thing that's kind of good to start keeping track of is that some molecules, some aldehydes and ketones have no alpha protons, some have one alpha proton, and some have two, and or even three. And we're going to see that that makes a difference in what they can do in terms of the aldol reaction as we go along. So now that we understand enolates, we can talk about this aldol reaction, because the aldol reaction is a reaction of an enolate. So let's go through the reaction we did in lab last time we met. I'll redraw the formation of the enolate. So, aldol reaction. So in our experiment, we started with propanal. So propanal looks like this. It's got a 3-carbon aldehyde with 2 protons in alpha positions. And we put this in with hydroxide. So first step is that hydroxide deprotonates the aldehyde or ketone, plucks one of the alpha protons off. And I'll draw it as this resonance structure. But the other one is just fine too, and you might see it drawn that way. You can draw the mechanism using either resonance structure. That one is just maybe a little easier to see how things happen next. So I have this reversible arrow here, which means that there's an equilibrium that's set up, and it doesn't strongly favor products. In other words, when you put hydroxide in with propanal, it's basic enough to deprotonate this a little bit, but it doesn't like completely go to products. So there's a little bit of this and a lot of leftover propanal, and that's important because this has something to react with now. It'll react with the propanal in the next step. So another molecule of propanal will get involved in the next step. So I'm going to draw another propanal over here. This is the same molecule that we started with over here on the left side. I'm just making this one orange so that it's a little easier to differentiate. And tell where all the atoms are coming from in this product that's going to be 2 of aldehydes coming together. So the lone pair on the enolate acts as a nucleophile, and it attacks the carbonyl carbon because there's partial positive charge there, and electrons get pushed up onto the carbonyl oxygen. And so this is a point where these two aldehyde molecules are going to come together. So we're making a carbon-carbon bond between the alpha carbon of one and the carbonyl carbon of another. And this is going to give us a molecule that's gotten a lot bigger. And I will draw this new carbon-carbon bond in two colors. I'll make it half white and half orange. There's an O minus here. There we go. Here's the original alpha position, and there's still an H there. And I'll put the H over here as well. So there we go. When the water or hydroxide does the deprotonation, it generates water. And there's always a lot of water around because usually there's water as a co-solvent or a solvent. We used 50% sodium hydroxide solution in water when we did this, so there was like half of the material that we threw in was water. So there's a lot of water around. And what happens in the next step is that water supplies a proton to that O minus. And what comes out of this is this species where we've got a neutral molecule we've made a new carbon-carbon bond, and this material looks like this. There's the original alpha position that was the enolate. This is called an aldol product. Aldol product. And the reason it's called that is because it has an aldehyde part and an alcohol part. Aldehyde, alcohol, hence aldol. The reaction works with ketones as well, so you don't always have an aldehyde. You might have a ketone functional group. We'll go through some examples of ketones, but this is an easy way to remember it, is you get this. And there is a bond between the alpha carbon of the original aldehyde that was the enolate, and then the beta carbon is the carbonyl of the second aldehyde equivalent. So we've got an alpha and a beta position here. And that's the aldol product. If you have at least one proton on your alpha position, if you're an aldehyde or ketone, you can do this aldol reaction. The thing about this molecule is there's a second one here. When the aldol product has an alpha proton, it can get plucked off again, and you can get another reaction to happen. This first sequence is the aldol reaction, but there is a dehydration reaction that can happen second, and that's what we're going to look at next. So you can have a second deprotonation because when you pluck an H off of water, you regenerate the hydroxide catalyst. And so that catalyst can deprotonate again. There's an alpha position here. That H is acidic, so it can go and grab that H, and that can give a new enolate structure. Which looks like this. Now there's a lone pair here. So this is a new enolate. And so that can happen. And the molecule has this built-in leaving group. This OH is a potential leaving group. Now, it's not a great leaving group, but if you look at what we're dealing with here, we're dealing with hydroxide as a base and hydroxide as a leaving group, so it's kind of a wash. You use hydroxide to deprotonate things, and then you can use hydroxide as a leaving group. You're not generating a much stronger base from a much weaker base. It's like you've got the same base strength, so energetically there isn't a big penalty for doing this. And so what happens in the next step, which is reversible, is that this negative charge, this lone pair, can swing in here and give the OH group a push. And this generates this new molecule that's got a double bond between the alpha and the beta positions. And I'll draw it half in white and half in orange to indicate the carbons that each part of the molecule came from. And then we've got an OH minus. So we regenerated the catalyst and the reaction can happen again. This is the dehydration step. So there's two separate reactions that are going on here. There's the aldol reaction, which is the first part. And then there's this deprotonation and dehydration reaction that happens in the second part. So in the dehydration, you get water out when this OH minus grabs the proton, you get H2O out of it. So there's the water from the dehydration step, and then we regenerate the catalyst in this step. So, so there's the product. Now the thing is the aldol reaction for aldehydes is pretty favorable, but the dehydration reaction isn't really very favorable. In other words, it doesn't go to product heavily. So what we had to do in our experiment was distill the products. We distilled this and water out of a reaction mixture to make the reaction go to products by Le Chatelier's principle. So we were able to collect lots of this. And tomorrow in lab, you're going to get your, you get your NMR spectrum data emailed to you today, and then we'll look at it in lab tomorrow before we do the lab practical exam. But that's the last thing we'll do in the lab is we'll study the spectrum of that molecule and see if we got all the correct signals for all the protons that thing has. So 2 steps. Aldol reaction, dehydration. Not all molecules can do that. So let's take a look at some examples of reactions where you can do one or the other or maybe none. And try to predict the products. I think this aldol business is one where drawing the mechanism, or at least part of the mechanism, is really helpful. It's always helpful, I think, in organic chemistry, but with aldol, I think it's worth drawing the enolate intermediate and then drawing the aldehyde or ketone carbonyl that it reacts with next to it and go through and use that to draw new bonds so that you can keep track of what's going on. All right, here is here's an aldehyde that, let's see if we can predict what happens with an aldol condensation reaction. This is one that's got a methyl, and a hydrogen in the alpha position, but it only has one hydrogen. All right, so let's put it in with hydroxide. Sodium hydroxide, or whatever hydroxide, deprotonates the alpha position and forms an enolate, and that's the first thing that happens in the aldol reaction. So you have to be able to do this. Form an enolate. That enolate has a resonance structure. I'm just going to draw it like this to keep the mechanism short, but there it is. Then the next thing that can happen is if you draw another molecule of the carbonyl compound, here's that aldehyde that we started with, the enolate carbon can attack the carbonyl carbon because there's partial positive charge on the carbonyl, and so this can come like this. Attack there, and then you get a new carbon-carbon bond. So this is the part that usually, if people get confused, this is usually where things kind of go sideways. figuring out where the connectivity is and what goes with what. So let's go through it and just make sure that we get it okay. So this is the alpha position. I'm going to draw that. Alpha position is right here. There are two methyl groups on the alpha position, so make sure you draw them on the alpha position. Then the alpha position made a new bond to the carbonyl of the other aldehyde, and there's that. So that's the intermediate, and this bond is the new bond that we made. The molecule had two of those getting together. Okay, and it's not quite at the aldol product stage yet, but we'll get there. So what will happen in the next step is that water supplies a proton to the O minus. So O minus grabs proton off of water, and that makes a neutral aldol product, which has got this structure. There's an alpha position and there's a beta position. So this is the aldol product. All right. Now, look at the alpha position and ask yourself, is there a proton there that could get plucked off to make a new enolate? There is not. It's two methyl groups. So that alpha position is out of protons. So this is where it stops. So reaction stops here. There is no dehydration here. Because there's no alpha position to deprotonate and make water from. So this is one where you'd isolate the aldol product. It'd be the expected product. In cases like where we looked at over here, I'll just like flash this one up on the screen one more time before I erase it. This aldehyde had two H's on it. And so one of them gets deprotonated, makes an enolate. You get an aldol product. The aldol product still has one left because there were two. So it can get deprotonated again, and you get a dehydration reaction. So on aldehydes or ketones that have two or more alpha protons, you get aldol and dehydration. If your aldehyde or ketone just has one alpha proton, then you just get the aldol reaction and not the dehydration. And if your aldehyde or ketone has no alpha protons, you get nothing. Basically, it doesn't work at all. Nothing happens because there's no alpha positions to deprotonate. So that's the story with these. Let's take a look at a couple of examples. I'm going to show you a ketone example just to make sure that you're exposed to it and have seen something like it before. Okay. So with ketones, the equilibrium doesn't really favor strongly the aldol product, but you can, there are methods you can use to try to get it to go that way. But let's take a look at this reaction. So this is a ketone. On the left side, there's a phenyl group which has no alpha protons. And I'm just putting that there to make this kind of a simple reaction so that we're not getting like enolates on two different sides of a carbonyl. Aldol reaction can get really complicated. If you've got a ketone with two different alkyl groups and they can both form enolates, you can get lots of different enolates and lots of different products. So I'm going to avoid those kinds of examples because they're confusing. And looking at this looks an awful lot like our propanol example. So I want to just maybe make it a little bit more diverse. Instead of phenyl, I'm going to put a tert-butyl here. It will get the same effect, but it will be just a little different. So if we put in hydroxide can deprotonate this. Aldehyde, ketone, there's a ketone now. We'll deprotonate the ketone in the alpha position and generate an enolate. And then, this is a strong nucleophile. It can attack another equivalent of ketone. Now, this is a pretty hindered ketone, so I don't know how fast this reaction is going to go. The tert-butyl group really is pretty bulky, and it would slow down the reaction, but let's just hypothetically assume it's going to work. All right, this comes in like this, attacks there, and now we have this molecule that's got a new bond between the aldehyde, or I'm sorry, the ketone carbonyl here and the alpha position of the enolate. The thing you got to keep track of is just that this carbon has 2 alkyl groups, whereas before it just had 1. All right, and then water supplies a proton to this intermediate. This is called an aldolate. It's not a term you need to remember, but there's a word for it, the deprotonated aldol product, and that gives, as the product, a species that's got a new bond between the two groups, and it's neutral. So we've got an OH, we've got a ketone here. So this is still technically called an aldol product, even though it's not an aldehyde, it's ketone, but it's a generic name. And that's the bond that we made overall. And the thing about this is that there is another proton in that alpha position. So base can come by and pluck that off. Hydroxide can come by and grab that proton. You make a new enolate. And that enolate has this built-in leaving group, this OH group that can leave as hydroxide. So we've got our negative charge here. And then electrons swing in and give the leaving group a push. And the final product out of this two-step reaction, or two-part reaction, the aldol and the dehydration, is this species where there's a new carbon-carbon double bond. And there's a couple of different ways this could be arranged. You could have the tert-butyl group in this position, or you could have the ethyl and the tert-butyl flipped around. I'm not gonna be concerned about those stereoisomer products, but if you can get the connectivity, that's the big thing. So one of the things to look at and keep track of is that the double bond that you get when you do an aldol reaction and a dehydration product is always going to be between the alpha and the beta positions. So in the dehydrated aldol product, there's the carbonyl, the position next to it is alpha, and then the next position is beta. The double bond's always between alpha and beta. That's just the way these reactions work. Okay, so that's an example of a ketone reacting. A lot of times what you're going to be asked to do is to think about not just the reaction in the forward direction, like, here's a carbonyl compound and some base, figure out what products you get, aldol and dehydration reactions. But here's a product, figure out what aldehyde or ketone it would have to start from. So we're going to talk about these backward thinking reactions or retrosynthetic reactions, because there's some of these in the homework as well. And it's good to get some practice with them. They're not like inherently harder, there's just like a different approach to them, I'd say. But that knowing where that double bond is really helpful. In fact, these are, I think, a lot easier once you get the hang of it. Okay, so here's a reaction, or a product, I should say. Predict what carbonyl compound you would have to use to get this product in an aldol reaction followed by dehydration. In other words, tell me what carbonyl compound you have to put in with base to get this. So it's like a retrosynthetic arrow. I'll put over here aldehyde or ketone. So where do you start? This one isn't neatly labeled with white carbons and orange carbons. So, so you're going to have to remember what we talked about, how there's an alpha position and there's a beta position, and the double bond is between those. The trick is that that's where the bond forms. So the stuff on the left side is one of the carbonyl compounds, and the stuff on the right side of that line is the other carbonyl compound. And when it's a reaction between two identical carbonyls, that's the way it works. So this bit right here, the way this worked was, this was a ketone that had an enolate here, and then this was a ketone. It's the same ketone, really. I mean, it's just I'll draw it over here in exactly the same orientation. So the way this worked is there was an enolate that attacked another molecule of that same species, generated an aldol product, and then it dehydrated to form this. So identify where the double bond is. It's got to be next to the carbonyl, label alpha and beta, and then imagine slicing it in half where the double bond is, because that's where the new condensation reaction happened. So the ketone that you would need would be this one. You can draw it in whatever conformation you want. That's just the best one. Let's look at another example. Once you get the hang of these, like I said, I think you're going to find these easier than going in the other direction, like having an aldehyde or ketone and predicting the product. All right, let me think of a good one here. Just inventing a question here as we go along. So predict what kind of aldehyde or ketone you would need to make this molecule. Now this is one that doesn't have a double bond in it, but you can still use the alpha and the beta analysis. The carbonyl, start there, and then alpha position is the spot next to it. The beta position is the next carbon over that has the OH group. And this is an important thing. When you're looking at aldol reactions, the beta has to be the one that has the OH group attached. Don't label that as a beta position, because that's not where the bond formed. So once you have these identified, that bond between alpha and beta, that's the one that formed in the reaction, the aldol reaction. And so the part on the left, this part came from the enolate. And this part over here on the other side of the squiggly line came from carbonyl compound. In this case, it's an aldehyde. So if I was to go back one step and show you what this looked like, this is a reaction between an enolate that looks like this and an aldehyde that looks like this. And that's how you get back to there after a proton transfer reaction. Okay. One more thing is that sometimes aldol reactions happen in a crossed sense. What that means is maybe the enolate piece and the carbonyl piece aren't exactly the same. Those can get kind of complicated, but let's talk about a scenario where it actually doesn't. The simplest example I can think of a crossed aldol reaction. All the reactions that we've looked at so far, the aldehyde and ketone component forms an enolate and then attacks another molecule of the same aldehyde or ketone. But in a crossed aldol reaction, the pieces are different. So here's an example of one of those possible type structures. So here is an example of an aldehyde. And then, let's see. Here, for example. So what would happen if you put hydroxide base in with this? Well, what do you think about this one? Would you get any kind of reaction over here? No enolate over here. So this one doesn't form an enolate. This one would form an enolate, and so I'll draw that down here. And I'll say that this can form an enolate like this. Okay, and now this has the opportunity to either attack one of molecule that it started with, one of its own, or this one. And it could likely do both. But I'm going to show what happens if it reacts over here, because that's what the crossed aldol reaction is when the enolate attacks a carbonyl that isn't the same kind of carbonyl that it came from. So I think what I'll do is get rid of that reaction arrow and put one over here that shows there's an O- here now. This is the alpha position of the original enolate. So the enolate, this part came from the enolate. This part came from carbonyl that was attacked by the enolate. All right, and they're different, so that's why it's called a crossed aldol reaction. Okay, well, we can follow this through just like we would with a reaction that isn't crossed, and the next thing that happens is water puts a proton on this O-, and we get a crossed aldol product. So we got an OH up here, an aldehyde over here. There's the alpha position, there's the beta position. There are still two H's on that alpha position, so this is, I'm going to label this as this is a crossed aldol product. But this one's subject to dehydration because it's got the H's in the alpha position. So what can happen is hydroxide can pluck a proton off here of one of these alpha positions. And we get this new enolate structure, NH2O, and then in the next step, the leaving group leaves with a little help from that negative charge, and that gives this product. And it regenerates the OH- catalyst that was needed in the reaction, and the reaction can continue. This molecule is called cinnamaldehyde. And it's in cinnamon. So if you like cinnamon, and this time of year everybody puts cinnamon on everything, it seems. It's in all sorts of different holiday-themed drinks and dishes and such. Actually, we just made some squash soup last night that's got cinnamon in it. We used a cinnamon stick, but you could stick cinnamon in. But if you wanted to make artificial cinnamon flavor that was just like, you know, the original, or just like the original, you could do it with this synthesis scheme and make cinnamaldehyde, and the positions are right there. So if somebody were to ask you a question of like, how could you make cinnamaldehyde using a crossed aldol reaction? Well, what you do is identify alpha and beta, carbonyl, and then alpha and beta. Go like that and say, okay, well, that would have to be the enolate piece, and this would have to be the aldehyde or ketone piece. It's an aldehyde in this case because there's an H there. But that would be how you could deconstruct it and say, I can make this via aldol reaction dehydration. So that's pretty much all you need to know about aldol reaction and dehydration reactions. And there's a lot more chemistry that can be done with them. It's really pretty complicated stuff, and you could talk a whole course about aldol reaction. Obviously, we're not going to do that here, but you at least get an introduction to it. It's a very important reaction biologically speaking too. There's a lot of natural products that are made using aldol chemistry. It's a reaction that Mother Nature likes when making big complicated molecules. So you'll see like the recurring themes of carbonyl, alpha, beta, double bond, for example, or over here, carbonyl, and then beta hydroxy carbonyl compound. Lots of those in natural products and found in nature. So, Okay, that's good for this lecture. So I'll see you, probably most of you in lab tomorrow, and we'll do the last lab meeting of the semester.